14 million light-years from Earth, Hubble examined what appeared to be an empty patch of space. But hidden in the darkness was an enormous cloud of hydrogen with no visible stars, no glowing galaxy, and far more gravity than the matter we can see should produce. It may be a galaxy that never ignited, suspended inside an invisible halo of dark matter. Before this journey begins, like the video, subscribe to the channel and join us as we explore the weirdest thing Hubble has ever seen. Earth rests inside a broad and layered universe, surrounded first by the solar system, then by the Milky Way, then by a loose gathering of galaxies known as the local group. Beyond that familiar region, the distribution of matter becomes a wide landscape of galaxy groups, filaments, and quiet spaces. Gravity gathers stars into galaxies and galaxies into larger associations, while enormous regions between them remain thin and dark. At this scale, even nearby objects lie across distances that human experience cannot easily hold. Light from the moon reaches Earth in a little more than 1 second. Light from the sun requires about 8 minutes. Light from the nearest star beyond the sun travels for more than 4 years. The light arriving from Cloud 9 begins its journey roughly 14 million years before it reaches the telescopes near Earth. 14 million light-years is a small distance compared with the full observable universe, yet it is far beyond the Milky Way and its immediate companions. The observable universe extends for tens of billions of light-years in every direction when cosmic expansion is taken into account. Against that immense scale, Cloud 9 belongs to the nearby universe. Astronomers use this phrase for a region close enough for individual galaxies, star-forming regions and faint structures to be examined with unusual detail. Nearby does not mean physically close in ordinary terms. It means that the light has crossed millions rather than billions of years, carrying a comparatively clear record of local cosmic structure. The path toward Cloud 9 leads away from the bright disk of the Milky Way and into a part of the sky containing the spiral galaxy Messier 94. This galaxy lies in the northern constellation Canes Venatici, a sky pattern used to organize positions as seen from Earth. A constellation does not represent a true physical group. Its stars may stand at very different distances, while the galaxies appearing between them lie much farther away. The apparent pattern serves only as a map. Within that map, Messier 94 appears as a compact island of light, its glow formed by many billions of stars blended across a distance of roughly 14 million light-years. Messier 94 is a spiral galaxy, though its structure differs in several ways from the broad, open form often used to represent spirals. Its central region shines strongly, surrounded by a bright inner ring and a more extended outer disk. Dust gas, old stars, and younger stellar populations occupy different parts of the system. The galaxy is smaller than the Milky Way, but it remains a large gravitational structure with a long history. Its visible disk forms only part of its full extent. Far beyond the bright starlight, gravity continues through a broad halo that contains thin gas and a much larger amount of unseen matter. The space around a galaxy is not completely empty. It may contain isolated stars, small satellite galaxies, streams of material diffused hydrogen and traces of earlier interactions. Much of this surrounding matter is extremely difficult to detect because it produces little visible light. A bright galaxy therefore appears to end where its starlight fades, even though its physical influence continues farther outward. The outskirts of Messier 94 lie within this dim transition. The crowded central light gives way to a sparse region where ordinary photographs show fewer structures, and where the boundary between the galaxy and intergalactic space becomes gradual rather than sharp. Cloud 9 occupies this broad, outer environment. Its position on the sky lies near Messier 94, separated from the bright center by a distance large enough to place it beyond the main stellar disk. At the distance of the galaxy, the projected separation is measured in hundreds of thousands of light years. Projected separation describes the distance across the plane of the sky. It does not, by itself, reveal whether one object lies in front of another or far behind it. For that reason, apparent closeness on an image is not enough to prove a physical connection. Astronomers must compare motion distance and surrounding structure before treating two objects as neighbors in space. The available measurements place Cloud 9 at approximately the same cosmic distance as Messier 94. Its motion along the line of sight is also similar to the motion of the galaxy. These facts support the view that Cloud 9 belongs to the same local environment, rather than being an unrelated foreground object. The association is strong, though the exact three-dimensional position remains less direct than the position drawn on a flat sky map. Cloud 9 may sit within the extended gravitational region of Messier 94, where the galaxy's influence reaches through space that appears almost vacant. From Earth, this entire setting occupies a narrow direction against a much deeper background. The foreground begins inside the Milky Way, where scattered stars and dust stand relatively close. Farther away lies Messier 94 and the space around it. Beyond that galaxy, many more distant systems fill the same line of sight. Their light crosses far greater distances before passing through the nearby region and reaching Earth. A single image can therefore contain several layers of cosmic time. Bright points may be stars within the Milky Way, soft patches may be remote galaxies, and empty-looking areas may still contain thin matter held by gravity. The distance to Cloud 9 also places its present appearance deep in the past. The light and other signals now reaching Earth leave the region about 14 million years ago. During that interval, early human ancestors have not yet appeared. Modern continents continue moving, and many generations of stars elsewhere complete parts of their lives. The object itself continues to exist in a later state that cannot yet be observed from Earth. This delay applies to every distant astronomical target. Telescopes do not see the universe at one universal moment. They receive layers of history with more distant regions appearing at earlier times. At the outermost level, Cloud 9 is therefore a small feature within a large nearby cosmic landscape. It stands beyond the Milky Way, beside a spiral galaxy whose gravity shapes an extended and mostly dark domain. Its distance is immense by terrestrial standards, but modest within cosmology. Its location is defined not by a bright boundary, but by the gradual fading of one galaxy into the sparse matter around it. Before its internal nature can be considered, its setting remains the first essential fact. Cloud 9 belongs to the quiet shore of Messier 94, where visible structure grows faint and the surrounding universe begins to look empty. Messier 94 appears from Earth as a bright spiral system set against a field of foreground stars and distant galaxies. Its visible light comes from a compact central region, a luminous ring and a broader disk whose outer parts become increasingly faint. The galaxy does not stop where the last obvious stars disappear. Gravity continues far beyond the bright surface, holding a wide halo of dark matter and a thinner population of ordinary matter. This extended region forms the outer environment in which Cloud 9 is found. The setting is quiet compared with the crowded inner galaxy, but it is not empty. Weak gravity, diffuse gas, and the motions of small surrounding systems still carry the influence of Messier 94 across a large volume of space. The galaxy lies about 14 million light-years from Earth. At that distance, its starlight reaches modern telescopes after travelling since a time long before the present human world. Cloud 9 appears close to it on the sky, but apparent closeness alone cannot establish a physical connection. The sky is a flat projection of a universe with depth, a nearby cloud, a distant galaxy, and a star within the Milky Way can occupy nearly the same direction while remaining widely separated in space. Astronomers, therefore, compare several kinds of evidence before deciding whether Cloud 9 belongs to the surroundings of Messier 94. The first clue is position. Cloud 9 lies outside the main visible disk in the sparse region beyond the bright rings and spiral structure. If it shares the distance of Messier 94, its separation from the galactic center is measured in hundreds of thousands of light-years. That scale places it far beyond most of the galaxy's stars, while still allowing it to remain inside the larger gravitational domain. Large galaxies commonly possess extended halos reaching well past their luminous disks. These halos contain dark matter, thin, hot gas, small companions, and material that has entered or left the galaxy over long periods. The position of Cloud 9 is consistent with an object residing in such an outer halo. Position remains only a two-dimensional measure, so motion provides another clue. Gas in Cloud 9 produces a measurable shift in its radio emission. This shift reveals motion toward or away from Earth along the line of sight. Messier 94 has its own measured line of sight motion. The two values are similar enough to support a common environment. An unrelated object could share a similar velocity by chance, yet the combination of nearby sky position and compatible motion makes a physical association more likely. Observations therefore indicate that Cloud 9 is not a local feature within the Milky Way and not a remote background system far beyond Messier 94. Distance estimates add further support. The cloud does not contain a known population of stars that can be used as standard markers, so its distance cannot be measured in the same direct way as the distance to many galaxies. Its placement instead depends on the evidence connecting it with Messier 94. The galaxy has a well-established distance from measurements of its stellar populations and other indicators. Once Cloud 9 is treated as a companion or halo object, the same approximate distance gives its observed angular size a physical scale. The cloud then occupies a region several thousand light-years across rather than a small nearby patch or an enormous distant structure. The outer space around Messier 94 also contains a thin intergalactic medium. This medium consists of matter spread so widely that individual particles may travel large distances before interacting. Even such sparse material can influence a gas cloud moving through it. The effect resembles pressure produced by motion through a fluid, though the cosmic fluid is extraordinarily thin. High-resolution observations show slight distortions in Cloud 9's gas, and these may reflect interaction with the surrounding medium associated with Messier 94. The evidence is suggestive rather than final. The distortions are small and other processes can shape diffuse gas. The gravitational relationship is also not measured as a simple orbit. Cloud 9's full motion through three-dimensional space remains unknown because observations mainly reveal its position on the sky and its velocity along the line of sight. Its sideways motion is too small to measure directly at such a distance with present data. Astronomers, therefore, cannot trace a precise path around Messier 94. The cloud may be bound to the galaxy passing through its extended halo or moving within the wider group environment. What is known is that its observed location and velocity fit naturally within the nearby system, rather than requiring a separate distance setting. Messier 94 itself belongs to a loose collection of galaxies. Such groups are less crowded than massive galaxy clusters and contain fewer large members. Gravity still links their motions across millions of light years, while the space between them contains dark matter and very thin gas. Cloud 9 sits within this broader neighborhood as well as near the spiral galaxy. The distinction matters because an object in a group can respond to more than one gravitational influence. Messier 94 is the nearest dominant visible structure, but the surrounding distribution of matter also contributes to the local environment. At this outer level, Cloud 9 is defined mainly by context. It lies in the same direction at a compatible velocity and at an infrared distance matching Messier 94. Its placement beyond the bright disk does not isolate it from the galaxy. Instead, it places the cloud within a region where gravity remains strong enough to organize matter even when starlight becomes scarce. The association is supported by several observations, though its exact depth and path remain uncertain. Cloud 9, therefore, occupies the dim outskirts of a nearby spiral system, suspended in the broad transition between a visible galaxy and the nearly empty space surrounding it. There, the orderly brightness of the inner galaxy gives way to a faint gravitational landscape where distance is inferred from shared motion and location. Within that landscape, Cloud 9 remains close enough to Messier 94 for the two objects to be considered physical neighbors in space. The first sign of Cloud 9 does not come from visible light. It appears instead in radio observations of neutral hydrogen, a form of hydrogen in which each atom keeps its electron. Neutral hydrogen is common throughout galaxies and surrounding space. It can remain difficult to see because cold gas gives off little visible glow. Its presence becomes measurable through a faint radio signal produced when the orientation of the electron and proton changes inside the atom. This emission has a wavelength of about 21 centimeters and allows astronomers to map hydrogen that would otherwise remain hidden against the darkness of space. Radio telescopes collect this weak emission across regions of sky. Their large dishes or linked arrays measure changes in radio brightness and separate the signal by frequency. Because the frequency shifts when gas moves toward or away from Earth, the observations reveal both location and line-of-sight motion. A cloud can therefore appear as a concentration of hydrogen with a distinct velocity even when ordinary photographs show no corresponding object. Cloud 9 emerges in this way not as a luminous patch, but as a signal occupying a narrow range of position and motion near Messier 94. The detection begins within surveys searching for neutral hydrogen beyond the bright bodies of known galaxies. Such surveys scan wide areas because diffuse clouds may lie far from stellar disks. They record radio emission from the Milky Way, nearby galaxies, and more distant systems along the same directions. Astronomers separate these layers by examining velocity. Gas inside the Milky Way usually follows patterns connected with the rotation and structure of the local galaxy. Cloud 9 appears at a velocity inconsistent with nearby galactic gas and more compatible with the environment of Messier 94. The signal therefore points to an object millions of light years away. Its radio emission is faint, yet it repeats across independent measurements and extends over neighboring positions. This spatial continuity matters because random instrumental noise tends to appear irregularly. A true astronomical source remains connected across the sky and across frequency channels. Cloud 9 displays this kind of organized pattern. The hydrogen signal forms a diffuse body rather than a single isolated point. Its measured velocity changes only slightly across the detected region, showing that the gas belongs to one coherent structure rather than several unrelated clouds accidentally aligned along the same line of sight. Once the radio source is identified, optical images of the same area are examined. Deep photographs contain many objects, including stars within the Milky Way and galaxies far behind, Messier 94. None of them forms an obvious stellar system matching the position, shape and scale of the hydrogen emission. No central glow marks a galaxy. No population of young blue stars traces active star formation. No diffuse sheet of old starlight follows the radio boundary. The gas still occupies a place that appears almost blank in visible light, even though the radio data clearly show that a substantial amount of hydrogen is present. This absence is unusual because most large neutral hydrogen concentrations are connected with stars. In spiral galaxies, hydrogen spreads through disks where gravity, cooling, and compression allow parts of the gas to form dense molecular clouds. Stars are born inside those colder regions, and their light makes the host galaxy visible. Smaller gas-rich galaxies can be extremely faint, but they normally contain at least some older stars or scattered sites of recent formation. Cloud 9 differs because the detected hydrogen has no clearly associated stellar population in images. Its identity, therefore, cannot be assigned through ordinary galactic appearance. The radio signal also distinguishes Cloud 9 from a reflection dust patch or distant cluster of galaxies. Dust affects visible and infrared light but does not create the characteristic neutral hydrogen emission at the same velocity. A background galaxy may contain hydrogen, yet it would usually appear smaller in angle if it lay much farther away, and its velocity would differ from that of Messier 94. The measured signal remains broad on the sky and tied to the nearby galactic environment. These properties support the interpretation of a real gas cloud rather than an optical illusion or unrelated background source. Astronomers estimate the amount of neutral hydrogen by measuring the total strength of the radio emission and applying the inferred distance. At the distance of Messier 94, the signal corresponds to 1 million times the mass of the Sun in neutral hydrogen. This is a large reservoir compared with ordinary interstellar clouds inside the Milky Way, though it remains small compared with the gas mass of a major spiral galaxy. The estimate depends strongly on distance because a more remote object must emit more strongly to produce the same observed signal. The association with Messier 94 therefore provides the scale needed to interpret the detection. The gas is not observed as a sharply bounded sphere. Radio maps have limited resolution and the emission fades gradually toward the edges. The brightest part marks where neutral hydrogen is most concentrated, while weaker emission spreads outward until it becomes difficult to distinguish from noise. The object's full extent therefore depends partly on the sensitivity of the observations. More sensitive measurements reveal lower density gas farther from the center. Even with these limits, Cloud 9 clearly occupies a region many thousands of light years across, showing that the signal does not arise from a compact object such as a star or a small planetary system. At this stage, the most direct fact is simple. A coherent mass of neutral hydrogen exists near Messier 94, and visible light does not reveal a matching galaxy. Radio astronomy provides the evidence because hydrogen atoms preserve a weak but measurable signature, even in darkness. The cloud is known first through frequency, motion, and position, rather than through shape and color. Its detection demonstrates that matter can remain organized on galactic scales without producing an obvious field of stars. In the empty-looking sky beside a nearby spiral galaxy, the radio signal gives substance to a region that visible images alone would leave unnoticed. The radio signal of Cloud 9 gives astronomers a precise region to examine with visible light telescopes. The field appears quiet in ordinary images, yet the absence of an obvious galaxy does not prove that no stars are present. A very faint stellar system can hide below the limits of shallow surveys, especially when its stars are spread across a broad area. Hubble, therefore, studies the same position with much greater sensitivity and sharper resolution. Its task is not to photograph the hydrogen directly because cold neutral gas produces little visible light. Instead, it searches for individual stars or a diffuse glow that might belong to the cloud. Hubble observes from above Earth's atmosphere, where air no longer blurs incoming light. Its mirrors focus distant objects into narrow points, allowing faint sources to be separated from one another. This resolution becomes essential in a crowded extragalactic field. Many objects appear within the same patch of sky, but most do not belong to Cloud 9. Some are foreground stars inside the Milky Way. Others are remote galaxies lying far beyond Messier 94. A true stellar population associated with the cloud would need to share a consistent distribution, distance, and concentration rather than appearing as scattered, unrelated points. The images reach deeply enough to reveal numerous faint background galaxies. Their forms vary from compact smudges to small, elongated systems, each carrying light that has traveled from much greater distances. These background objects demonstrate that Hubble is looking through the region rather than encountering an opaque mass of dust. If Cloud 9 contained thick dust, it could hide objects behind it and complicate the search. Instead, distant galaxies remain visible across the field. The cloud is therefore transparent in visible light, consistent with a diffuse body of hydrogen containing little material capable of blocking starlight strongly. Astronomers compare the locations of the detected optical sources with the radio outline of the hydrogen. A genuine stellar component would likely become more numerous towards the cloud's central region or follow the broader shape of the gas. No such pattern appears. The faint points and small galaxies remain distributed in ways expected for ordinary foreground and background populations. Their positions do not trace the neutral hydrogen. The apparent objects within the cloud's boundary are therefore not evidence of a hidden galaxy. They are mainly chance alignments produced by the depth of the universe along one direction. Hubble can also search for resolved red giant stars. A red giant is an evolved star that has expanded and brightened after using much of the hydrogen in its center. These stars are useful in nearby galaxies because they can remain visible even when lower mass stars are too faint to detect. If Cloud 9 contains an old stellar population similar to that of a small dwarf galaxy, some red giants may rise above the detection limit. The images do not reveal a concentration of such stars at the cloud's location. This absence places a strong limit on the total amount of hidden starlight. The search also considers diffuse emission. A galaxy made of many unresolved faint stars can produce a smooth background glow even when individual members cannot be separated. Astronomers measure the brightness of the sky across the hydrogen region and compare it with neighboring areas. No clear excess follows the cloud. The result indicates that Cloud 9 lacks both a detectable group of bright stars and a broader sheet of unresolved light. Any stellar population that exists must therefore be extremely sparse and faint compared with the amount of hydrogen revealed by radio observations. This conclusion depends on careful removal of instrumental and natural background effects. Hubble images contain faint signals from detector noise, scattered light, cosmic rays, and the combined glow of distant, unresolved sources. Multiple exposures help identify temporary marks while calibration corrects variations across the detector. Astronomers also model the general sky level before searching for a weak, extended feature. These steps do not create certainty at every point, but they reduce the chance that a small fluctuation will be mistaken for starlight belonging to Cloud 9. The remaining field still shows no convincing optical counterpart. The distance of Messier 94 determines how faint the cloud stars would appear. At roughly 14 million light-years, bright giants remain within Hubble's reach, while stars similar to the Sun are much harder to detect individually. The observations therefore cannot rule out every possible star. A few low-mass stars may exist without being seen. What the images exclude is a normal stellar population, with the brightness expected for a typical dwarf galaxy containing the measured amount of gas. Cloud 9 remains far darker than such systems at the same distance. The deep optical field also clarifies the difference between emptiness and invisibility. The region is not empty because radio measurements show hydrogen spread across thousands of light years. It is not visually blank in an absolute sense because many distant galaxies appear behind it. Yet none of the visible structures matches the cloud itself. Hubble separates these layers and turns an apparently simple patch of darkness into a precise comparison between gas and starlight. The telescope's strongest result is not the discovery of a luminous object, but the confirmation that the expected light is missing. This contrast gives the observation its unusual power. Hydrogen occupies the foreground, remote galaxies remain visible behind it, and no intervening population of stars fills the measured space. Within the boundaries traced by neutral hydrogen, the optical sky remains dominated by unrelated sources. No central concentration, stellar ring diffuse disk, or group of bright giants identifies a hidden galaxy. The cloud allows background light to pass through while contributing almost none of its own. Hubble therefore strengthens the interpretation that Cloud 9 is a large gas-bearing object without a detectable stellar body. The observation does not reveal what holds the gas together or why stars have failed to form. It establishes only the visible condition of the field. At the location marked by radio emission, the universe remains optically open, deep, and unexpectedly dark. Cloud 9 does not appear in radio maps as a perfect circle or sharp border. Its neutral hydrogen forms an uneven body whose brightness fades gradually into the surrounding sky. The central region is easier to detect because more hydrogen atoms lie along the line of sight. Farther outward, the signal weakens as the gas becomes thinner. The boundary, therefore, depends partly on the sensitivity of the telescope. A deeper observation can trace hydrogen beyond the edge seen in a shallower map, while a less sensitive survey records only the denser inner portion. This gradual fading is expected in a diffuse cloud. Gas particles do not stop at a fixed wall. Their density decreases over distance as pressure, gravity, and the surrounding environment shape the outer layers. In radio images, this produces contours that spread outward like soft rings rather than hard outlines. The contours are not evenly spaced, and they do not remain symmetrical around the center. One side of Cloud 9 appears more compressed, while another extends into a weaker, longer feature. The cloud shows a directional form rather than the shape of an isolated body in space. The compressed side is marked by a steeper change in hydrogen density. Radio brightness falls more quickly there, suggesting that the gas is being pressed inward or that the cloud has encountered a denser region of its environment. The effect is slight. Cloud 9 is not torn apart and its main body remains coherent. Still, the sharper edge differs from the slower fading seen elsewhere. Such asymmetry can arise when a gas cloud moves through thin surrounding material. Even a sparse medium can exert pressure if the relative motion continues over a long period. This kind of pressure is called ram pressure. It develops when an object moves through gas and feels the combined impact of particles along its leading surface. In ordinary experience, air presses against a moving vehicle. Around galaxies, the surrounding gas is vastly thinner, but the distances and times are much larger. A cloud traveling through a galactic halo can slowly lose or rearrange material at its outer edge. The leading side becomes compressed while gas removed from the opposite side can trail behind. The physical principle remains simple even though the environment is almost empty. Cloud 9's faint extended feature resembles a tail. It contains less neutral hydrogen than the main body and is harder to detect with confidence. Its shape points away from the compressed region, matching the general pattern expected if the cloud is interacting with surrounding gas. The tail does not prove this process by itself. Irregular structure can also result from internal motion, past disturbance, uneven gravitational forces, or the original way the gas accumulated. Observations indicate that environmental pressure is plausible while the exact history of the shape remains uncertain. The outer form also depends on the state of the hydrogen. Radio telescopes detect neutral atoms, not all hydrogen present. At low density, ultraviolet radiation can remove electrons from hydrogen atoms, producing ionized gas that no longer gives the same 21 centimeter signal. The visible radio edge may therefore mark a change in atomic state rather than the true end of the cloud. Neutral hydrogen can fade where radiation becomes strong enough to keep the thin outer layers ionized. Beyond the detected boundary, more gas may continue in a form that is difficult to map with the same observations. This effect can make the cloud appear smaller and more sharply shaped than its gas distribution. The denser regions shield part of their interior from ionizing radiation, allowing neutral hydrogen to survive. The thinner outskirts receive more radiation and become ionized. If external pressure compresses one side, the higher density, there may preserve a narrow, neutral edge even while material is being pushed. On the opposite side, stretched gas may fall below the density needed to remain neutral, causing the radio tail to fade before all matter disappears. Radio resolution also influences the measured shape. A telescope does not record every hydrogen atom separately. It combines emission from an area of sky into each image element. Fine structures smaller than that area become blurred together. A sharp knot, narrow filament, or small gap may therefore appear as a smooth patch. Higher resolution observations reveal more detail but may become less sensitive to very broad, faint emission. Astronomers compare data collected at different resolutions to distinguish real structure from effects produced by the instrument. Cloud 9's main body remains compact enough to stand apart from ordinary diffuse gas. In the larger environment, its emission connects across multiple positions and velocity channels, showing that the structure is physically coherent. The compressed edge and faint extension occur within this organized pattern. They are not isolated patches placed randomly around the cloud. Their velocities remain close to that of the central gas, which supports the idea that they belong to the same object. The shape is therefore a property of Cloud 9 rather than a chance overlap of unrelated hydrogen features. The uneven boundary provides a quiet record of forces acting over long periods. Gravity draws the gas inward. Internal pressure resists collapse radiation, changes the outer atoms, and motion through surrounding material may reshape the surface. None of these effects needs to be violent. A weak influence sustained across millions of years can leave a compressed side and a fading wake. The cloud's appearance is therefore not fixed. It reflects a balance that can shift as density, motion, and environment change. At this layer, Cloud 9 is seen as a diffuse body with an asymmetrical skin. Its neutral hydrogen grows denser toward the main region, falls steeply along one edge, and stretches weakly along another. The outline remains partly defined by telescope sensitivity and by the point where hydrogen becomes ionized. Even so, the broad pattern is clear enough to show that the cloud does not rest in complete isolation. Its outer form carries signs of contact with the thin medium around Messier 94, while preserving the uncertainty required by limited data. The outer hydrogen of Cloud 9 exists beneath a constant field of ultraviolet radiation. This radiation does not come from one nearby star or one bright galaxy. It fills intergalactic space as a weak background produced by many distant sources. Hot stars, active galactic nuclei, and earlier generations of luminous objects contribute photons energetic enough to remove electrons from hydrogen atoms. Across immense distances, their combined light forms a faint but persistent bath. The field is weak compared with sunlight near Earth. Yet Cloud 9's outskirts are extremely thin, so even a small supply of energetic photons can determine the state of the gas. Hydrogen becomes ionized when a photon carries enough energy to separate the electron from the proton. The atom then changes from neutral hydrogen into a positively charged proton and a free electron. Radio observations at a wavelength of about 21 centimeters trace only the neutral form. Ionized hydrogen can occupy the same region without producing that particular signal. The apparent radio boundary of Cloud 9, therefore, does not necessarily mark the edge of all its gas. It marks the place where neutral atoms become too scarce for the radio emission to remain detectable. Density controls how deeply ultraviolet radiation penetrates. In the outermost layers, hydrogen atoms are widely separated and the radiation reaches them easily. Ionization removes electrons while collisions between free electrons and protons sometimes restore neutral atoms. The balance depends on temperature density and the strength of the radiation field. At low density, recombination proceeds slowly because particles rarely meet. Ionization then dominates, leaving most hydrogen electrically charged. As the gas becomes denser, inward recombination becomes more frequent and neutral. Hydrogen begins to survive in larger amounts. The cloud can also shield itself. A sufficiently thick column of neutral hydrogen absorbs ionizing photons before they travel far into the interior. The outer atoms receive most of the radiation and form an ionized layer, while gas behind them remains partly protected. This process is called self-shielding. It does not create a solid surface. Instead, the fraction of neutral hydrogen rises gradually as the incoming radiation weakens with depth. The transition can still appear fairly narrow in radio maps because the 21 centimeter signal grows rapidly. Once enough neutral atoms collect along the line of sight. Ultraviolet radiation also supplies heat. When a photon removes an electron, some of its energy becomes motion, shared among particles. Repeated ionization, recombination, and collisions maintain the thin outer gas at temperatures that are often near 10,000 degrees Celsius. This gas is hot in terms of particle motion, though it would not feel dense or fiery. Its pressure remains low because so few particles occupy each volume. Temperature and density act together, and a thin, hot layer can press gently against cooler, neutral material farther inside. The heated outer gas resists compression. Its particles move in many directions, producing pressure that tends to make the cloud expand. Gravity pulls inward while the surrounding medium may press from outside. Ultraviolet heating, therefore, becomes one part of a broader balance. If the gas loses heat efficiently, it can contract and grow denser. If radiation continues, replacing the lost energy, contraction slows. In a small gravitational system, this heating may be enough to keep much of the gas spread out rather than allowing it to settle into compact, cold structures. The strength of the ultraviolet background changes over cosmic history. In the early universe, the first stars and active galaxies ionize much of the hydrogen between galaxies during a period known as reionization. After that transformation, intergalactic space remains exposed to ionizing radiation, though the intensity evolves as the population of luminous sources changes. Cloud 9 is observed in the nearby universe, where the present background is weaker than during some earlier periods. Even now, its outer layers remain vulnerable because their density is low and their self-shielding is limited. Local radiation from Messier 94 may also contribute, but the cloud lies far beyond the galaxy's bright, stellar disk. Most ionizing photons produced by young stars are absorbed within the galaxy before escaping into the halo. Some can travel outward, especially through directions where gas and dust are thin. The exact contribution at Cloud 9's position is uncertain. Observations support the presence of the general cosmic ultraviolet background, while the importance of additional radiation from the nearby galaxy depends on escape paths, distance, and the galaxy's recent star formation. The ionized layer remains difficult to observe directly. It may emit extremely faint optical lines when electrons recombine with protons, but the surface brightness can fall below practical detection limits. Absorption against a bright background source can reveal ionized material along a narrow path, though suitable sources are not always available. As a result, estimates of Cloud 9's full gas content rely partly on models. The detected neutral hydrogen gives a secure lower amount, while the unseen ionized portion may add substantially to the total. Its exact mass and extent remain uncertain. The transition is not fixed at one radius. A small change in density, pressure, or radiation intensity can move the neutral boundary inward or outward. Gas compressed by motion through the surrounding halo may become better shielded, while gas drawn into a thin extension may become ionized. The radio shape can therefore change even when the total amount of hydrogen changes little. What appears as a structural edge is partly an atomic boundary maintained by slowly changing conditions. Radiation shapes the cloud without producing a dramatic, visible glow. It changes atomic states, maintains warmth, and defines where radio observations can follow neutral hydrogen. The process operates continuously across the diffuse surface. Photons arrive from the wider universe, electrons separate from protons, and the outer gas becomes transparent to the radio method that first reveals Cloud 9. Deeper layers contain enough material to weaken the radiation and preserve neutral atoms. The cloud's observable outline, therefore, emerges from a quiet transition between exposed ionized gas and self-shielded hydrogen formed by the steady interaction of matter with the ultraviolet background of space. The neutral core of Cloud 9 occupies the region where hydrogen becomes dense enough to resist ionization. Beyond it, ultraviolet radiation keeps much of the gas electrically charged and difficult to trace through the 21-centimeter signal. Within it, atoms collect in numbers large enough for self-shielding to work. The radio emission strengthens the outline, becomes more definite, and the cloud begins to reveal an interior structure. This core is not a solid body. It remains a thin, extended volume of gas, but it contains the clearest concentration of ordinary matter associated with Cloud 9. At the distance of Messier 94, the neutral region extends across several thousand light-years. This scale is much larger than a typical cold cloud inside the Milky Way, and much smaller than the stellar disk of a large spiral galaxy. The size places Cloud 9 between categories. It is too broad to resemble one star-forming cloud, yet it lacks the visible stars that usually make a gas-rich dwarf galaxy recognizable. Its measured diameter depends on the sensitivity and resolution of the radio observations, because the neutral signal fades gradually towards the outside. The core contains roughly 1 million times the mass of the Sun in neutral hydrogen. This estimate comes from the strength of 21-centimeter emission combined with the assumed distance. Each atom contributes a minute signal, but the combined emission from an immense number of atoms becomes measurable. The calculation remains tied to distance. If the cloud were much nearer, its mass would be smaller, while a more distant location would imply a larger reservoir. Its association with Messier 94 gives the most consistent scale and places the neutral mass near 1 million solar masses. Most of this mass is spread thinly. Even in the central region, Cloud 9 does not reach the densities found inside molecular clouds where stars normally form. Radio maps measure the amount of neutral hydrogen along the line of sight rather than the density at every point. This is called column density. A high column density can result from a thick path through thin gas or a shorter path through denser material. The observations show that the central column is greater than the surrounding values, but it remains low compared with active star-forming regions. The core is therefore neutral without being cold and compact. Neutral hydrogen can exist across a range of temperatures. Some atoms may belong to a warmer phase near several thousand degrees Celsius, while smaller portions may be cooler. The radio data place limits on the state, but do not resolve every thermal component. A narrow radio feature can indicate cooler gas or less internal motion, while a broader feature can indicate warmer gas or more varied motion. Within Cloud 9, the central hydrogen remains comparatively quiet and diffuse, rather than divided into obvious dense knots. Hydrogen alone does not guarantee star formation. The gas must cool contract and gather into structures with much greater density. In many galaxies, heavy elements and dust help remove heat and protect molecules from radiation. Cloud 9 may contain very little of these materials, though their abundance is not established. If the gas is poor in heavy elements, cooling becomes less efficient and dust shielding becomes weak. The neutral core can then persist for long periods without reaching the conditions needed to build cold molecular clouds. The distribution of the central gas is smooth on the scales resolved by current observations. No bright radio clumps stand out as clear sites of collapse. The strongest emission remains broad rather than concentrated into compact peaks. Smaller structures may exist below the resolution limit, but they cannot contain enough neutral hydrogen to dominate the observed map. This smoothness supports the view that the core is a stable, low-density reservoir rather than a collection of active stellar nurseries. The radio image records matter that has gathered yet has not proceeded into the usual visible stages of galactic development. Self-shielding becomes most effective near the center because the path through hydrogen is longest there. Ionizing photons entering from outside are absorbed through the surrounding layers, reducing the radiation reaching deeper regions. The neutral fraction rises and 21 centimeter emission becomes stronger. This relationship creates a core whose radio brightness reflects both total gas density and protection from radiation. The central signal does not necessarily mark a separate object inside the cloud. It marks the region where physical conditions allow neutral atoms to become the dominant detectable form. The core also contains helium, although the radio line used to map Cloud 9 traces hydrogen. Helium forms part of ordinary cosmic gas and adds mass that is not included when astronomers quote only the neutral hydrogen amount. Ionized hydrogen outside the radio boundary adds more unseen, ordinary matter. The true gas mass is therefore larger than the measured neutral component. Models estimate the additional material by considering radiation density and pressure, but the exact correction remains uncertain. The value near 1 million solar masses is a secure description of the detected neutral reservoir rather than the entire supply of gas. Across several thousand light-years, this reservoir remains almost completely dark at visible wavelengths. Its atoms produce radio emission without forming a bright, stellar population. Background galaxies can still be seen through the region, because the gas is too thin and dust poor to block much light. The core is therefore substantial in mass but transparent in appearance. Its presence becomes clear only when observations are tuned to the weak atomic transition of neutral hydrogen. Within Cloud 9, the neutral core represents the deepest layer directly mapped as ordinary matter. It is broad, smooth, self-shielded, and low in density. Roughly 1 million solar masses of detectable hydrogen occupy a volume extending across thousands of light years, yet no compact stellar structures emerge. The core demonstrates that gas can collect on a galactic scale while remaining too warm, too diffuse, or too chemically simple for efficient star formation. Its radio brightness reveals concentration without luminosity, substance, without an ordinary galaxy, and an interior shaped by the quiet survival of neutral atoms. The neutral hydrogen inside Cloud 9 does not remain perfectly still. Every atom moves because of temperature, pressure, and the weak gravitational forces acting across the cloud. Radio observations record these motions through changes in frequency. Gas moving toward Earth shifts the hydrogen signal slightly upward in frequency, while gas moving away shifts it downward. By separating the emission into narrow frequency channels, astronomers measure how velocity changes across the cloud. The resulting pattern shows a structure with a limited spread of motion without the orderly rotation often seen in ordinary gas-rich galaxies. In a rotating galaxy, one side generally approaches Earth while the opposite side recedes. The difference forms a smooth velocity gradient across the disk. This pattern reveals organized motion around a common center and allows the enclosed mass to be estimated. Cloud 9 does not display a clear gradient of this kind. Its measured velocities remain close to one another across the main neutral region. Variations appear, but they do not form the balanced pattern expected from a rotating disk. The absence of obvious rotation suggests that the gas is supported in another way, or that any rotation is too weak to dominate the observations. The width of the radio line provides another measure of motion. A perfectly motionless and cold group of hydrogen atoms would produce a very narrow signal. Real gas creates a broader feature because atoms move in different directions and at different speeds. Thermal motion contributes to this width with warmer gas, producing a wider line. Turbulence, expansion, contraction, and unresolved flows can add further broadening. In Cloud 9, the line remains narrow, indicating that the gas does not contain strong turbulence or rapid large-scale movement. Its internal state appears remarkably calm compared with many active galactic environments. A narrow line does not mean that every atom moves slowly. Hydrogen at several thousand degrees Celsius still carries substantial microscopic motion. The measurement instead shows that the range of line-of-sight velocities remains modest when averaged across the telescope beam. Warm gas can therefore produce a quiet radio profile if the cloud lacks powerful shocks, strong rotation, or violent outflows. The observed width places an upper limit on temperature when thermal motion is assumed to dominate. If turbulence contributes part of the width, the true temperature can be lower than that limit. Cloud 9's velocity field also remains coherent. Neighboring regions emit at similar frequencies, showing that the gas belongs to one connected system. Random foreground clouds would produce unrelated velocities and disconnected shapes. The close agreement across the neutral core supports the interpretation of a single object. Small shifts from one area to another may reflect gentle internal flows, mild compression, or changes along the line of sight. These variations remain limited enough that the cloud preserves a common motion through the environment of Messier 94. The lack of strong rotation distinguishes Cloud 9 from many dwarf galaxies. Even small galaxies often show some ordered movement when their gas settles into a flattened structure. Rotation balances part of the inward pull of gravity and prevents rapid collapse. Cloud 9 instead appears more nearly pressure-supported. In a pressure-supported system, random particle motions push outward in all directions while gravity pulls inward. The overall structure can remain stable without forming a rotating disk. This arrangement is common in hot gas clouds and some rounded stellar systems, though the details depend on density and mass. Pressure support can arise from both temperature and non-thermal motion. Thermal pressure comes from the random movement of particles. Additional support may come from weak turbulence, magnetic fields, or motions too small to resolve. The radio line measures only the component of velocity directed along the line of sight, so it does not reveal every form of movement. Astronomers therefore use models to connect the observed width with the three-dimensional state of the gas. These models indicate that the narrow motions are consistent with a diffuse cloud held in a shallow gravitational potential. The outer asymmetry can also affect the velocity pattern. A compressed edge may contain gas slowed or redirected by interaction with the surrounding medium. A faint tail may carry material moving slightly differently from the central core. Current measurements show only modest differences, and the available resolution limits detailed interpretation. The signal from several regions can blend within one telescope beam, smoothing narrow streams or small knots into a single average. Higher resolution observations may reveal finer structure, but the broad calmness of the cloud remains established. The velocity spread helps constrain the mass needed to hold the gas together. If the cloud contained only the detected neutral hydrogen, thermal motion could allow it to expand over time unless outside pressure confined it. A larger unseen mass would deepen the gravitational field and help retain the gas. The measured motions are therefore important because they connect observable hydrogen with the strength of the surrounding potential. A broad line would require stronger gravity or indicate disturbance. The narrow line points toward a gentle but persistent confinement rather than a highly massive, rapidly moving system. Uncertainty remains because the cloud's geometry is not fully known. A nearly face-on rotating disk could hide much of its rotation from line of sight measurements. An elongated cloud viewed from one angle could also produce a misleadingly narrow velocity range. Observations do not support a clear disk, but they cannot exclude every orientation or structure. The simplest interpretation remains a pressure-supported cloud with little ordered rotation, while more detailed data are needed to test alternatives. Within the neutral core, motion therefore appears restrained, and coherent hydrogen atoms move enough to maintain pressure, yet the cloud lacks the broad rotation, turbulence, and shocks common in luminous galaxies. Its radio signal stays narrow across thousands of light-years, preserving a shared velocity with only gentle internal variations. The gas behaves less like a spinning galactic disk and more like a diffuse atmosphere resting inside an unseen gravitational environment. Its quiet motion becomes a central clue, showing that Cloud 9 is not merely dark, but dynamically unusual as well. Cloud 9 can remain together only if its outward pressure is balanced by forces that prevent the gas from dispersing. The neutral hydrogen is warm and constantly moving, even though its radio signal shows only a narrow range of velocities. Those microscopic motions create pressure in every direction. Left without confinement, the cloud would slowly expand. Its density would fall and ultraviolet radiation would ionize a larger fraction of the gas. The continued presence of a compact neutral core therefore indicates that some combination of gravity and external pressure restrains the hydrogen across thousands of light years. Gas pressure arises from the random motion of particles. Faster particles strike surrounding regions more often and transfer more momentum, producing stronger pressure. Temperature measures much of this motion, while weak turbulence can add an extra contribution. In Cloud 9, the observed radio line gives an estimate of the internal velocity spread. That spread is modest, but it is still large enough to resist the gravity produced by the detected neutral hydrogen alone. The cloud, therefore, cannot be understood simply as a self-gravitating ball made only from the gas seen in radio observations. The surrounding medium may provide part of the confinement. Thin gas in the outer halo of Messier 94 can press against Cloud 9 from outside. This pressure is extremely weak by terrestrial standards, yet the cloud is also extremely diffuse. A small external force maintained over a vast surface can influence its size and density. The compressed edge supports some interaction with the environment. Even so, outside pressure by itself may not explain the full structure, especially if the cloud remains stable while moving through regions where the surrounding density changes. Gravity offers a more persistent form of confinement. Every part of the cloud attracts every other part, but the measured hydrogen mass produces only a shallow gravitational field. Helium and ionized hydrogen add ordinary matter, increasing the total gas mass beyond the neutral amount. These additions help, but models indicate that the visible gas still provides too little gravity to hold the cloud in its observed state under many reasonable conditions. A deeper gravitational potential is therefore considered one produced mainly by matter that emits no detectable light. Dark matter is the name given to this unseen mass. It does not absorb or emit ordinary light in measurable amounts, but its gravity affects gas stars, galaxies, and larger cosmic structures. In Cloud 9, dark matter is not observed directly. Its presence is inferred from the way the hydrogen can remain compact while maintaining internal pressure. If the cloud lies inside a small dark matter halo, the gas can settle into the halo's gravitational well. The center becomes denser, the outer layers become thinner, and the whole system can remain bound without strong rotation. The balance between pressure and gravity is called hydrostatic equilibrium. In such a state, pressure decreases outward while gravity pulls inward. Each layer supports the weight of gas above it, much as the lower atmosphere of a planet supports the thinner layers at higher altitude. Cloud 9 is far more diffuse than a planetary atmosphere, yet the same principle applies. The gas does not need to remain completely motionless. It can contain thermal movement and small flows, while its average structure changes only slowly. Models of hydrostatic equilibrium begin with the measured distribution of neutral hydrogen. They include temperature, ionization, external pressure, and an assumed gravitational field. The model then calculates how gas density should change with distance from the center. A shallow potential allows the cloud to spread widely, while a deeper potential keeps it compact. By comparing these predictions with the observed radio profile, astronomers estimate what kind of hidden mass distribution can support the hydrogen. The result is not a unique measurement because several combinations of temperature geometry and external pressure can produce similar shapes. The cloud's uncertain three-dimensional form adds further difficulty. A sphere-flattened body or elongated structure can appear similar when projected onto the sky. Each geometry changes the relation between column density and true volume density. The internal temperature is also not known at every location. A cooler core requires less gravity for confinement, while warmer gas requires more. Small amounts of unresolved turbulence can imitate thermal broadening. For these reasons, estimates of unseen mass depend on assumptions that must remain clearly stated. Even with these uncertainties, the pressure balance provides a useful test. If Cloud 9 contains no dark matter, it must rely heavily on external pressure or exist only briefly before dispersing. A short-lived cloud could still be observed, but its coherence and smooth internal motion would then require a recent origin or continuing replenishment. If it occupies a dark matter halo, long-term survival becomes easier to explain. The gas can remain bound for extended periods, while radiation and environmental pressure shape only its outer layers. The inferred gravitational field does not need to be enormous. Cloud 9 shows no rapid rotation or broad velocity spread, so the potential must remain relatively shallow. A massive galaxy-sized halo would accelerate the gas more strongly and likely produce different motions. The favored picture involves a small halo, one with enough gravity to retain diffuse hydrogen, but not enough to force the gas into a dense, rotating disk. This intermediate state matches the calm radio profile and the broad central concentration. Pressure and gravity therefore meet in a delicate balance. Thermal motion pushes the hydrogen outward, external material presses gently inward, and an unseen gravitational field may hold the cloud together from within. The exact share of each influence remains uncertain, but the observed structure rules out complete freedom. Cloud 9 behaves as gas resting inside confinement, not as an unbound patch drifting toward disappearance. Its stability is written in the smooth decline of density, the narrow spread of velocity, and the persistence of a neutral core. Across the cloud, this balance remains gentle, extended, and measurable only through patient observation of faint hydrogen. Through these quiet measurements, invisible gravity becomes a physical possibility rather than an abstract idea. The absence of visible stars in Cloud 9 is not established by a single empty image. It comes from a careful comparison between what Hubble detects and what a normal faint galaxy should contain at the distance of Messier 94. A dwarf galaxy can spread its stars across a large area and remain difficult to notice as a smooth glow. Hubble reduces this problem by resolving the brightest individual stars. If Cloud 9 contains an old stellar population, some evolved stars should appear above the detection limit and gather statistically around the neutral hydrogen. The most useful expected members are red giant stars. These stars have exhausted much of the hydrogen in their central regions and have expanded into luminous, cool objects. Their brightness allows them to be detected across millions of light years, even when smaller stars similar to the Sun remain invisible. In a faint, nearby dwarf galaxy, red giants usually form a loose but measurable concentration. Their colors and brightnesses also follow patterns that distinguish them from many foreground stars and remote galaxies. Hubble searches the Cloud 9 field for this population and finds no convincing excess. The field still contains numerous points and small patches of light. Some points are stars in the Milky Way lying far closer than Cloud 9. Many patches are distant galaxies whose compact forms can resemble stars when they are extremely faint. Astronomers classify these objects by shape, color, and brightness, then compare their distribution inside the radio boundary with nearby control regions. A hidden stellar system should raise the number of suitable sources near the cloud. The measured counts remain consistent with the ordinary mixture of foreground and background objects. This statistical approach matters because no single faint source can be accepted as a member. A star and a remote compact galaxy can occupy the same position by chance. Membership becomes persuasive only when many sources share a common spatial concentration and a brightness pattern appropriate for one distance. Cloud 9 provides neither sign. The objects seen through its position do not cluster around the hydrogen center, and they do not create a recognizable sequence of stars at the distance of Messier 94. The optical field remains indistinguishable from the surrounding sky. Hubble also places limits on younger stars. Recent star formation would produce bright blue stars, short-lived, massive stars, or compact groups associated with dense gas. These objects are luminous and would be easier to detect than an ancient population of low-mass stars. No such blue concentration appears. No luminous stellar knot follows the highest neutral hydrogen column. No ionized nebula marks radiation from newborn massive stars. The absence of these features indicates that Cloud 9 is not presently forming stars at a rate comparable with known gas-rich dwarf galaxies. An older population could still be extremely sparse. Hubble cannot exclude every low-mass star because most would fall below the detection threshold at 14 million light-years. A few isolated stars might therefore exist without altering the image. The important limit concerns total stellar mass. If Cloud 9 contained a conventional dwarf galaxy population, its brightest giants and its combined diffuse light would become measurable. Since neither appears, the amount of starlight must remain far below that expected for a typical galaxy holding a similar neutral hydrogen mass. Astronomers express this result through an upper limit rather than an absolute statement of 0 stars. An upper limit is the greatest amount that can remain hidden without contradicting the observations. Its value depends on assumptions about the age and chemical composition of any unseen population. Old metal-poor stars produce one pattern of brightness, while younger stars produce another. Models generate expected star counts for different populations, and these predictions are compared with the Hubble field. Across reasonable assumptions, the permitted stellar component remains very small. Surface brightness provides a second constraint. Even when individual stars are too faint to resolve, their combined light can create a smooth glow. Astronomers measure the background across the cloud and search for a broad increase aligned with the radio emission. This work requires careful correction for scattered light detector variation and the unresolved background of distant galaxies. No matching diffuse structure is found. The result agrees with the star count analysis and shows that Cloud 9 lacks both a concentrated population and an extended sheet of ordinary starlight. Dust cannot easily explain the missing stars. Background galaxies remain visible through the cloud, showing that the region is largely transparent. A thick dust layer capable of hiding a dwarf galaxy would also dim or redden those background sources. Radio observations reveal diffuse hydrogen, but the column is too low to imply strong optical extinction. Cloud 9 therefore appears dark because little light is produced within it, not because a luminous system is concealed behind an opaque screen. The ratio between gas and stars becomes unusually large. In ordinary dwarf galaxies, even gas-rich examples contain a detectable history of star formation. Their oldest stars record earlier episodes that may have ended long ago. Cloud 9 shows no comparable record. Its neutral hydrogen is therefore not merely between bursts of activity in an otherwise visible galaxy. Observations indicate that any previous star formation must have been extremely limited, leaving no population that Hubble can identify with confidence. The result is not a failure of detection, but a measurement in its own right, because every missing giant star lowers the amount of ordinary luminous matter that the cloud can contain. This absence narrows the scientific interpretation. Cloud 9 cannot be treated as a normal dwarf galaxy whose stars are simply faint in shallow surveys. Hubble reaches the brightness range where the upper part of such a population should emerge. The continued blankness places the object in a more unusual category, one dominated by gas and whatever unseen mass may confine it. Uncertainty remains at the level of a tiny stellar component, but the central conclusion is stable. Within the neutral hydrogen boundary, visible stars contribute almost nothing to the known structure, and the cloud remains optically dark even under Hubble's deep examination. Cloud 9 contains ordinary matter that radio telescopes can measure, but the detected hydrogen cannot easily explain the cloud's continued coherence. Roughly 1 million times the mass of the Sun appears in neutral hydrogen. Additional ordinary matter exists as helium and ionized gas, yet these components still leave the system dominated by something that produces no visible light. The missing mass is not identified from a photograph. It is inferred from the relationship between the cloud size, internal motions, temperature, and ability to remain confined across thousands of light years. Mass reveals itself through gravity. A body does not need to shine for its gravitational influence to act on surrounding matter. In galaxies, stars and gas move faster than visible matter alone can explain. In galaxy clusters, the motions of members and the bending of background light indicate far more mass than telescopes see. Cloud 9 presents the same general principle on a smaller scale. Its hydrogen behaves as though it rests within a gravitational field deeper than the gas can create by itself. The inference begins with the measured line width. Hydrogen atoms possess thermal motion, and the radio signal records a narrow but definite range of velocities. These motions supply pressure that tends to spread the cloud outward. The observed gas extends only several thousand light-years and remains centrally concentrated. If its own detected mass provides the only inward pull, models often predict a structure that is more weakly bound or more extended than the observations allow. Adding unseen mass strengthens gravity without adding starlight and produces a more stable concentration. External pressure may assist this confinement, but it cannot be measured precisely enough to remove the need for gravity in the leading interpretation. The surrounding halo of Messier 94 contains thin gas that can press on Cloud 9, particularly along its compressed side. This influence may shape the boundary and limit expansion. However, a changing external environment would not naturally explain the smooth central density profile by itself. A gravitational potential centered on the cloud provides a persistent inward force that acts throughout the gas. Dark matter offers the simplest known source of that potential. Dark matter interacts through gravity and appears to contribute most of the mass in many galaxies. It does not produce detectable starlight, and it does not need to gather into stars or cold clouds. In the standard cosmological picture, dark matter forms halos before ordinary gas settles into them. Many small halos are expected to remain almost invisible if their gas never forms stars. Cloud 9 matches the observable conditions of such a system, although its dark matter cannot be detected directly. Models fitted to its hydrogen distribution suggest a total halo mass near several billion times the mass of the Sun. One commonly discussed value is about 5 billion solar masses. This number is not a direct weighing of the cloud. It depends on assumptions about distance, gas temperature, geometry, ionization, external pressure, and the form of the gravitational field. Different assumptions change the infrared total. The estimate, therefore, describes a plausible mass scale rather than a precisely established quantity. The model distinguishes gravitational mass from gas mass. Gas contributes to both pressure and attraction, while dark matter contributes mainly to attraction. When the calculated gas profile is compared with the observed radio brightness, the visible material alone cannot reproduce the compact form under the preferred thermal conditions. The unseen component supplies the additional inward acceleration. This comparison does not reveal individual dark matter particles. It reveals only the amount and arrangement of gravitating material required for the gas to occupy its measured state. The contrast between neutral gas and total mass is extreme. A neutral hydrogen mass near 1 million solar masses forms only a tiny fraction of a halo measured in billions of solar masses. Ionized hydrogen and helium increase the ordinary component, but dark matter still dominates strongly in the model. Such dominance explains why the object can possess substantial gravity while remaining nearly transparent. The matter responsible for most of the attraction neither blocks background galaxies nor adds its own visible glow. The absence of stars makes the inference unusually clean in one sense and unusually difficult in another. In a normal galaxy, stellar motions can trace the gravitational field at different distances from the center. Cloud 9 offers no stellar traces. Its hydrogen becomes the only known material responding to gravity, and its motion is gentle rather than rotational. Astronomers must therefore infer mass from pressure balance and gas structure instead of from a clear rotation curve. This method carries larger uncertainties, but it still places meaningful limits on possible interpretations. A cloud without enough total mass would gradually disperse unless the surrounding pressure remained finely adjusted. A system with too much mass would compress the gas more strongly, increase internal speeds, and possibly encourage cooling and collapse. Cloud 9 occupies a narrow middle range. Its gravity appears sufficient to retain gas, but not sufficient to produce the dense conditions associated with visible star formation. The unseen mass must therefore be considered together with the measured quietness and broad extent of the hydrogen. Alternative explanations remain possible. Cloud 9 could be a temporary gas feature confined mainly by its environment or its true distance, and geometry could differ from the preferred assumptions. A small stellar population could also remain below current limits, though it would not provide enough mass to explain the infrared gravity. Observations indicate that a dark matter-dominated halo offers the most consistent account, while further measurements are required to reduce the uncertainty. The mass that cannot be seen is therefore known through consequence rather than light. It shapes the density of hydrogen counters' internal pressure and allows a starless cloud to persist as a coherent object. The estimate remains model-dependent, but the imbalance between luminous matter and required gravity is substantial. Cloud 9 appears not as an empty patch with a little gas, but as a gravitational system whose visible component forms only a thin trace of its total substance. Inside Cloud 9, the unseen gravitational field is often described as a dark matter halo. A halo is a broad concentration of matter surrounding a center, with density generally increasing inward and declining outward, unlike a luminous galaxy. This structure does not reveal itself through stars, dust lanes, or glowing gas. Its shape must be inferred from the response of the neutral hydrogen resting within it. The gas acts as a faint tracer, showing how strongly gravity must pull at different distances if pressure and gravity remain close to balance. The simplest models treat the halo as nearly spherical. This assumption does not mean that every small dark matter halo must form a perfect sphere. Cosmic halos can be elongated, uneven, or disturbed by nearby structures. A spherical model is used because Cloud 9 offers only a limited two-dimensional gas map and a narrow set of velocity measurements. With no stars and no clear rotation, there are too few independent traces to reconstruct a complex three-dimensional shape. The spherical approximation, therefore, provides a controlled starting point rather than a direct image of the invisible structure. One common model uses a density profile known as the Navarro-Frenk-White profile. It is named after the researchers who identified its general form in simulations of cold, dark matter. In this profile, density rises steadily toward the center and falls through the outer halo. The profile is described mainly by total mass and concentration. Concentration indicates how strongly the halo mass gathers toward the inner region compared with its outer boundary. A more concentrated halo creates a deeper central pull, while a less concentrated halo spreads its mass across a broader volume. Early modeling places Cloud 9 within a halo containing roughly 5 billion times the mass of the Sun. The same modeling gives a concentration near values expected for small halos in the standard cold, dark matter picture. These results reproduce several broad features of the observed hydrogen, including its compact, neutral core and limited internal motion. The numbers remain estimates rather than direct measurements. They depend on the assumed distance to Messier 94, the thermal state of the gas, the surrounding pressure, and the chosen form of the dark matter profile. The inner density is especially difficult to determine. Radio observations show the projected distribution of neutral hydrogen, not the dark matter itself. The gas profile is affected by ultraviolet radiation, which changes hydrogen between neutral and ionized states. It is also affected by temperature, because warmer gas spreads farther in the same gravitational field. A broad, neutral core can therefore indicate a shallow inner halo, warmer gas, stronger outside pressure, or some combination of these conditions. Several physical arrangements can create nearly the same radio appearance. Some analyses find that Cloud 9 appears slightly more extended than expected under a standard centrally rising profile. If its distance and gas properties are correct, this difference may suggest that the inner dark matter density is flatter than the usual model predicts. A flatter center is often called a core. In a cored halo, density remains more nearly constant across the innermost region instead of continuing to rise steeply. Such a structure would produce weaker central gravity and allow gas to occupy a broader distribution. The evidence for a core is not conclusive. A smaller distance would reduce the physical size inferred from the angular image and could bring the gas closer to the standard profile. Environmental pressure may also change the outer distribution in ways that simple isolated models do not include. Recent simulation studies show that local surroundings and gas self-shielding can influence attempts to recover halo mass and concentration from neutral hydrogen alone. These effects can create biases even when the general hydrostatic picture remains valid. Mass and concentration can also trade against one another in the modeling. A heavier halo with a lower concentration may produce a gas profile similar to that of a lighter halo with greater concentration. This is called a degeneracy, meaning that different parameter combinations fit the same limited observations. Information about the external gas density can reduce the ambiguity because surrounding pressure affects how far the cloud extends. Without an independent measurement of that environment, the detailed inner structure remains less secure than the broad conclusion that substantial unseen mass is present. Cloud 9 provides no stars whose motions contest the central field. It also lacks a rotating disk that could reveal enclosed mass through orbital speed. Gravitational lensing is far too weak to map such a small halo with present observations. The hydrogen distribution therefore carries nearly the entire available signal. Better radio resolution can sharpen its central profile and separate temperature from unresolved motion. More sensitive observations can trace weaker neutral gas, while absorption measurements may constrain ionized material and the conditions surrounding the cloud. The dark matter halo is therefore understood as a range of permitted structures rather than a completed map. Its total mass probably lies on a scale of billions of solar masses, while its inner density may follow a standard rising profile or a flatter form. Observations clearly indicate that the detected gas represents only a small fraction of the gravitating system. They do not yet determine the exact shape of the invisible center. The outer boundary of the halo is theoretical rather than visible. Astronomers often define it as a radius enclosing matter at an average density relative to the universe. Cloud 9's gas occupies only the central portion of that volume. Most of the infrared dark matter extends far beyond the detectable neutral hydrogen, remaining untraced by direct emission. Within this hidden interior, gravity remains quiet and indirect. It does not produce light, a surface, or a visible boundary. It appears through the way hydrogen gathers, spreads, and maintains equilibrium. The neutral core becomes a delicate instrument resting inside the halo, responding to forces that cannot be photographed. Cloud 9 therefore offers a rare view of dark matter through simplicity, while preserving uncertainty about the detailed arrangement of the mass that holds its gas. Cloud 9 may represent a kind of system whose development is limited by reionization. Reionization is the period when the first generations of stars and galaxies fill the young universe with energetic ultraviolet light. That radiation removes electrons from much of the hydrogen between galaxies, changing the cosmic gas from a mostly neutral state into an ionized one. The process begins several 100 million years after the Big Bang and continues over an extended interval. By the time it is largely complete, small dark matter halos face a new environment in which ordinary gas is warmer, more exposed, and harder to retain. Before reionization, hydrogen can fall into shallow gravitational wells more easily because much of the Earth's surrounding gas is cooler. A small dark matter halo attracts this material, allowing density to rise near its center. The gas does not immediately become a galaxy. It must still cool, contract, and form dense structures before stars appear. Even so, the early supply of relatively cool hydrogen gives the halo a chance to gather ordinary matter. Cloud 9 may preserve part of such an early reservoir held inside a halo that never progresses far enough to create a visible stellar population. As ultraviolet radiation strengthens, the conditions change. Ionized gas reaches temperatures near 10,000 degrees Celsius, and the increased thermal motion makes it harder for weak gravity to hold the particles. Large halos remain capable of pulling gas inward, but smaller halos lose part of their supply or fail to capture additional material. The boundary between success and failure is gradual rather than fixed. It depends on halo mass formation, time, local radiation, strength gas, density, and the history of nearby structures. A halo near this threshold can retain some gas while remaining unable to compress it efficiently. This state is described as reionization limited because cosmic radiation restricts the amount and density of gas that the halo can keep. The term does not mean that reionization alone determines every feature. Gravity, cooling chemical composition, and environmental pressure still matter. Reionization provides a lasting source of heat and ionization that changes the balance. In Cloud 9, the broad ionized envelope and small neutral core fit a system in which only the densest central gas can shield itself from the background radiation. The effect continues long after the main reionization era ends. The universe remains filled with an ultraviolet background produced by galaxies and active galactic nuclei. Its intensity changes over time, but it does not disappear. A small halo that fails to form stars early cannot simply return to its earlier condition. Warm surrounding gas remains difficult to accrete while the material already inside stays partly ionized. The halo can therefore persist for billions of years with a limited gas supply and no strong path toward stellar formation. Simulations of cosmic structure predict many small dark matter halos. Most form as larger systems grow through gravity and mergers. Some become satellite galaxies, some lose gas, and some remain almost dark. Reionization strongly influences which of these outcomes occurs. Halos below a certain range of gravitational depth tend to contain few stars or none at all. Their ordinary matter fraction can fall far below the average cosmic value because heated gas escapes or never settles. Cloud 9's inferred halo mass places it near the regime where this suppression becomes important. A reionization-limited cloud is not identical to a stripped galaxy. A stripped galaxy begins with stars and gas, then loses material through interaction with a larger neighbor or surrounding medium. Such a system should usually retain an old stellar population even after most gas disappears. Cloud 9 shows no detectable stars, so a history dominated by stripping does not naturally explain its darkness. Reionization limitation instead allows the halo to remain starless from the beginning, preserving gas without ever building a conventional galaxy. The surviving hydrogen must occupy a narrow range of conditions. If density becomes too low, ultraviolet photons keep nearly all of it ionized, and the neutral radio signal fades. If density rises enough, self-shielding allows a neutral core to form. If the gas contracts much further, cooling may accelerate and stars may begin to appear. Cloud 9 remains between these outcomes. Its center is dense enough to stay partly neutral, but too diffuse to show clear molecular clouds, young stars, or an older population left by earlier activity. The term relic also applies cautiously. A relic is a surviving remnant of an earlier cosmic state. Cloud 9 may preserve information about how small halos collect gas before and during ionization. Its present structure could reflect a long history of heating and limited accretion. However, observations do not directly reveal its condition billions of years ago. The relic interpretation follows from comparison with models, not from a recorded timeline. It remains uncertain whether the cloud formed exactly in this manner or whether later environmental processes also reshape it. Its location near Messier 94 may influence the balance without erasing the reionization signature. The galaxy's extended halo supplies external pressure that can help confine gas. Its radiation may add to the general ultraviolet field. Gravitational tides may also affect the cloud over long periods. These influences operate after the early universe has already limited the available material. Cloud 9 can therefore carry both ancient and local effects, with the neutral core representing the portion that survives them. Within this interpretation, the cloud is not an incomplete modern galaxy waiting for a sudden beginning. It is a system whose permitted development remains restricted by conditions established early in cosmic history. Dark matter gathers. First gas enters only partly. Ultraviolet radiation raises the pressure, and the central hydrogen settles into a stable, diffuse state. The process leaves a quiet object with enough gravity to hold matter, enough density to remain partly neutral, and too little cooling and compression to produce detectable stars. Its present form becomes a balance inherited from a hotter universe where small halos retain only the gas that pressure shielding and shallow gravity allow them to preserve over time. Cloud 9 contains hydrogen, gravity, and time, yet these ingredients do not automatically produce stars. Star formation begins only when gas reaches conditions that allow gravity to overcome pressure on small scales. The material must cool, gather, and divide into dense regions where collapse can continue. In ordinary galaxies, this sequence occurs inside cold molecular clouds. Cloud 9 remains outside that regime. Its hydrogen is spread across thousands of light years. Its internal motions are gentle, and its central density stays below the level commonly associated with sustained stellar birth. Density is the first barrier. A broad cloud can contain a large total mass while remaining thin at every location. Cloud 9 holds roughly 1 million solar masses of neutral hydrogen, but this material occupies an immense volume. The average distance between atoms remains large compared with the spacing inside star-forming clouds. Gravity acts across the entire system, yet local regions do not become massive enough to collapse independently. The gas, therefore, rests inside the dark matter halo, without breaking into compact knots where stars can begin. Cooling is the second barrier. Gas must lose energy before it can contract. As gravity draws material inward, particles accelerate and collisions convert motion into heat. If this heat remains trapped, pressure rises and resists further collapse. In enriched galaxies, atoms heavier than helium emit energy through many spectral lines, while dust grains help cool and shield dense regions. Cloud 9 may contain very few heavy elements and little dust. Its exact chemical composition remains uncertain, but the absence of stars suggests that enrichment has been limited. With fewer cooling channels, warm hydrogen can remain diffuse for long periods. Molecular hydrogen also plays an important role in cold star-forming gas. Molecules form efficiently on dust surfaces and survive best where surrounding material blocks destructive ultraviolet light. Cloud 9 offers weak shielding through most of its volume. Its neutral core protects some atoms from ionizing radiation, but that protection does not necessarily create the colder, darker conditions required for a large molecular cloud. Ultraviolet photons can continue breaking molecules apart, even where hydrogen remains neutral. The gas may therefore stay atomic rather than progressing into a dense molecular phase. External radiation maintains this stalled condition. The cosmic ultraviolet background supplies heat and keeps the thin outer gas ionized. Radiation reaching deeper layers becomes weaker, but it still influences the thermal balance. A small dark matter halo cannot compress the gas strongly enough to overcome this steady heating. The result is a warm central reservoir surrounded by a broader ionized envelope. The cloud remains bound, yet its particles carry enough thermal motion to prevent the gradual concentration that would raise density toward star-forming levels. The shape of the dark matter potential matters as well. Cloud 9's inferred halo is deep enough to retain gas, but shallow compared with the halos of luminous galaxies. Gravity gathers hydrogen toward the center, but the central pull does not become overwhelming if the inner dark matter density is relatively flat. The force rises gently across the core. Gas can then settle into a broad distribution rather than a compact central peak. This arrangement allows equilibrium without collapse, preserving a neutral cloud whose structure changes slowly. Rotation does not provide a path toward a dense disk. Many galaxies form when gas loses energy and settles into a flattened rotating structure. Collisions between gas streams remove random motion while angular momentum keeps the material from falling directly into the center. Over time, the disk develops regions where density becomes high enough for stars to form. Cloud 9 shows no clear ordered rotation. Its hydrogen behaves more like a pressure-supported atmosphere. Without a settled disk, the gas lacks the repeated compression produced by spiral structure, orbit crossings, and gravitational instability. The surrounding environment can compress parts of the cloud, but the observed influence remains weak. Ram pressure may sharpen one edge and stretch a faint tail, yet it does not appear to create dense knots. Stronger compression could, in principle, trigger cooling if gas were pushed above a critical density. The available observations show no bright clumps, young stars, or ionized nebulae. Environmental pressure, therefore, reshapes the outer layers without driving the interior into a new phase. It may even remove diffuse material and reduce the supply available for later collapse. Time alone does not guarantee ignition. A stable cloud can remain close to equilibrium for billions of years if heating pressure and gravity continue balancing one another. Small disturbances may pass through the gas and fade without producing lasting collapse. The absence of stars means there are no supernova, stellar winds, or heavy elements generated internally. This prevents the feedback and chemical enrichment that transform the interstellar medium of ordinary galaxies. Cloud 9 remains chemically and dynamically simple because it never begins the cycle that would make later star formation easier. This state separates the object from a faint galaxy experiencing a quiet interval. A dormant galaxy normally preserves older stars formed during earlier episodes. Those stars continue shining after the gas becomes inactive. Hubble detects no such population in Cloud 9. The evidence, therefore, supports a more complete failure of ignition, not merely a temporary pause. Any star formation that occurs must remain too limited to leave the luminous record expected from even a very small dwarf galaxy. Cloud 9 becomes a galaxy-shaped possibility without the defining event that makes a galaxy visible. Dark matter supplies a gravitational framework. Hydrogen gathers inside it. Radiation, low density, limited cooling, and weak compression prevent the gas from crossing the threshold into sustained collapse. The system remains neither empty nor luminous. It is a halo with matter structure and internal balance, but without the stellar population that normally announces its existence. Its long silence follows naturally from physical conditions that permit gas to survive while denying it the density and coldness required to ignite. Across its broad interior, every influence remains below the point where local collapse becomes irreversible, leaving hydrogen suspended in a lasting state between cosmic accumulation and stellar creation within darkness. Cloud 9 matters because it may reveal a population of cosmic structures that theory has long predicted, but observation has rarely confirmed. In the standard picture of galaxy formation, dark matter gathers first. Small halos form, merge, and grow. Ordinary gas falls into some of these gravitational wells, cools, and forms stars. Other halos remain almost invisible because their gas is removed, heated, or prevented from collapsing. Cloud 9 appears to occupy this hidden category, with enough gas to be detected and too few stars to resemble a normal galaxy. This possibility addresses a long-standing difference between theory and observation. Simulations of cold, dark matter produce numbers of small halos around galaxies. Telescopes detect far fewer luminous dwarf galaxies than the number of predicted halos. The difference does not necessarily mean that the halos are absent. It may mean that many never form enough stars to become visible. Radiation, shallow gravity, and environmental effects can leave them dark. Cloud 9 offers a rare chance to examine one through neutral hydrogen rather than through starlight. Its importance comes from being detectable without being luminous. A completely dark halo would reveal almost nothing unless its gravity affected another object or bent background light. Cloud 9 contains a neutral core that acts as a tracer inside the potential. The gas provides a measurable shape, velocity, spread mass, and response to external pressure. These properties allow models of halo mass and concentration to be tested. The cloud also tests models of ray ionization. Small halos respond strongly to the ultraviolet background created during the early universe. Simulations predict that some retain only a limited amount of gas, with a warm ionized envelope surrounding a denser neutral center. The predicted systems remain starless when their central density never becomes high enough for efficient cooling and molecular formation. Cloud 9 matches many of these features. Its measured, neutral core, optical darkness, and inferred halo mass place it near the boundary where ray ionization should suppress galaxy formation. A single object cannot establish an entire population. Cloud 9 may be unusual because of its specific environment near Messier 94. The surrounding halo gas may provide pressure that helps preserve the neutral core. Motion through that medium may compress one side and stretch another. If similar objects exist farther from large galaxies, they may contain less neutral hydrogen and become harder to detect. The cloud may therefore represent only the visible part of a broader class, selected because local conditions make its gas bright enough in radio emission. Future surveys can test this interpretation by searching for comparable hydrogen clouds around other nearby galaxies. Wide radio maps can identify faint neutral structures lacking optical counterparts. Repeated discoveries with similar masses, sizes, and motions would support the idea of a common, starless halo population. A failure to find them would suggest that Cloud 9 requires a rarer history or environment. The number and distribution of such objects can be compared with cosmological simulations, providing a test of how small halos retain ordinary matter. More detailed observations can also refine the nature of Cloud 9 itself. Improved radio resolution can map small changes in velocity and density across the core. These measurements can test whether the gas is truly pressure-supported or contains weak rotation hidden by present limits. Greater sensitivity can trace the faint neutral outskirts and clarify the compressed edge and tail. Absorption studies against background radio sources may reveal colder components or ionized material. Each measurement reduces the range of halo models that can reproduce the cloud. Chemical composition remains another important uncertainty. The abundance of elements heavier than helium can distinguish between nearly pristine gas and material previously processed inside stars. Very low enrichment would support a history with little or no star formation. Higher enrichment could indicate gas removed from another galaxy or mixed with material from Messier 94. Measuring this composition is difficult because the cloud emits little optical light. Suitable background sources may allow absorption lines to reveal the elements present along narrow paths through the gas. Alternative origins remain under consideration. The cloud could be debris from a past interaction, a fragment stripped from a faint galaxy, or a temporary condensation in the wider galactic environment. These possibilities must explain the lack of a detected stellar population, the calm velocity field, and the apparent need for additional gravity. Tidal debris often forms elongated streams and inherits chemical enrichment from its parent system. A pressure-confined condensation may not require dark matter, but it may be short-lived. Current evidence favors a dark halo, while the alternatives remain scientifically useful tests. Cloud 9 also sharpens the meaning of the word galaxy. A galaxy is usually recognized through stars, yet its gravitational foundation forms in dark matter before starlight appears. A starless halo containing gas occupies the boundary between a galaxy and a non-galactic cloud. Its classification depends on physical history rather than appearance alone. If the halo has the mass and structure expected for a dwarf galaxy but never forms stars, it can be described as a failed or dark galaxy. The term does not imply an intention or mistake. It describes a halted path of cosmic development. The weirdness of Cloud 9, therefore, lies in its combination of ordinary and missing features. It has hydrogen without visible star structure, without a luminous disk, and likely gravity without a directly seen source. Each property follows familiar physics, yet their combination is rare in observation. The object does not require unknown forces or exotic light. It requires only a small halo, limited gas, steady radiation, weak cooling, and time. Cloud 9 stands as a quiet test of how the universe builds many more gravitational structures than it illuminates. Its neutral hydrogen marks one hidden halo against the darkness near Messier 94. The remaining uncertainty is not a weakness of the object, but part of its value. Better measurements can change its interpretation, refine the mass, or reveal a different origin. For now, it remains a rare, visible trace of the unseen population predicted to surround galaxies throughout the nearby universe. Cloud 9 remains suspended in the darkness beyond the bright disk of Messier 94, a faint reservoir of hydrogen held within a much larger field of invisible gravity. Its radio signal crosses 14 million light-years and arrives as a quiet pattern of motion density and atomic light. Hubble looks into the same region and finds no galaxy of stars, only distant background systems shining through the cloud's transparent gas. The object does not glow-rotate strongly or gather itself into dense stellar nurseries. Its outer layers meet the ultraviolet background of the universe and become ionized. Its neutral center survives through self-shielding, gentle pressure and the pull of an unseen halo. Across thousands of light years, the hydrogen remains warm, diffuse, and calm. It rests near the threshold where matter can gather without fully becoming a luminous galaxy. The meaning of Cloud 9 remains open to further observation. It may be a reionization-limited halo, a starless relic, or a rare cloud shaped by the environment around Messier 94. Each explanation must account for the same simple facts. Gas is present, starlight is absent, gravity appears stronger than the visible matter alone can provide. Around it, the nearby universe continues in silence. Messier 94 turns slowly beneath its rings of stars. Thin gas fills the wider halo. Distant galaxies send their light through the field unchanged by the almost invisible object between them and Earth. Cloud 9 remains small against the cosmic landscape, yet it preserves a record of the structures that gravity builds and light never reveals. In that dark region, hydrogen waits without ignition, held in a long balance between radiation pressure and unseen mass.